It sounds impossible because there's no air in space, which means there's no sound either. However, the recording you're about to hear was created based on real vibrations of matter around a black hole. This is not music or a scientist's fantasy. This is real data, converted into an audible range. The result turned out to be so unusual that many compared it to a sound from a horror movie. But what is really happening near the most mysterious objects in the universe?
Just because you're not paranoid doesn't mean no one is watching you. Modern astronomers have decided not to wait for surprises from nature, so they closely monitor what is happening within the boundaries of the Milky Way and beyond. So, have there been any worthwhile discoveries? It turns out yes. Recently, the instruments detected an unidentified object that was emitting regular radio signals. It's hard to say what it is, but it clearly doesn't want to be detected. Hello, subscribe? Scientists first noticed the amazing space object 2 years ago. This was made possible with one of the most sensitive instruments designed to study the farthest corners of galaxies, arrays of antenna arrays in Australia. It is noteworthy that while working with this radio telescope, scientists repeatedly detected unknown objects and mysterious signals. After these inspiring discoveries, the research continued as more specific information was needed. For their work, astrophysicists used another device called Marion from the park's observatory. Unfortunately, it did not live up to expectations. No new data was obtained. Progress was made only this year. The South African radio telescope Meerkat confirmed that the previously discovered object does indeed exist, and in April, further evidence was provided by the ATCA instrument. The unexpected discovery is of great scientific value, because before this, it was practically impossible to get a clearer understanding of the mysterious object. It was as if it was avoiding being observed. Monitoring showed that it simply wasn't present in either the radio data archives or in X-ray or infrared studies. What do we know about this phenomenon at the moment? It was given the name GCGCRT J1745-3009. History. Researchers characterize the object as a transient radio signal coming from the center of the galaxy. The available astronomical data cannot shed light on the origin and structure of multi-wavelength objects similar to the one discovered. Simply put, this radio signal is unique in its characteristics. Most likely in the future, GCRT J1745-3009 will fall into a new class of cosmic objects and may not remain its only representative. This is because, with the help of more advanced technologies, scientists will continue to detect identical radio signals. What is remarkable about GCRT J1745-3009? The radio waves it emits are quite unusual. Their duration ranges from 2 to 4 weeks, and at the end of this period, the signal stops. But after some time it appears again. The phenomenon can be compared to blinking. Circular and linear distortions are also noticeable, which means obviously we are dealing with signal polarization. During the study of the strange object, the devices picked up signals exactly 13 times. At the same time, scientists emphasize that we still cannot determine exactly where these messages are coming from. The only thing that is known for sure is that it is not a pulsar with a powerful magnetic field. Initially, the theory seemed quite plausible, but further research disproved it. So what exactly are we dealing with? It is known that objects in the universe differ from each other by the length of their radio waves. The stars of some binary systems are located close to each other. If GCRT J1745-3009 were one of these celestial bodies, scientists would have been able to detect it much earlier. Also, the object cannot belong to supernovae since their properties are completely different. Therefore, the question of classification remains open for now. Space is an unpredictable place, and in recent years, a number of very unusual things have been found there. For example, the Hubble telescope recently took pictures of a region of a nebula called Herbig-Haro, specifically one of its objects, HH 111. It was captured by cameras sensitive to a wide range of wavelengths. The formation of the Herbig-Haro sector was influenced by young, highly active stars that sometimes emit ionized gases with very high temperatures. As a result, atoms lose their electrons and become electrically charged. What happens next? The ionized gas crashes into interstellar clouds made up of other gases and small particles. These processes occur near young stars and are characterized by incredible speeds. What can we learn from analyzing this information? Thus, scientists were able to find out how the region of Herbig-Haro objects originated, as well as to record phenomena whose lifespan is extremely short, just a couple of thousand years. If you study images of such nebulae closely, you can notice how they fly out at tremendous speed through the gas clouds, moving away from the main star. Significant changes are observed in these areas over the course of several years. For example, in certain locations, the brightness is much higher than in other areas. One of the Hubble telescope's cameras has high sensitivity, so it is able to detect even small waves that are not visible to the naked eye. As you know, there are very bright objects in Herbig-Haro, but it's difficult to assess the processes occurring there, to track them, because the view is obscured by an impenetrable dusty haze. This is where the WFC3 camera, which is installed on Hubble, comes into play, capturing waves that are able to penetrate through layers of dust. However, research is ongoing, so it's too early to draw any conclusions. Those are far from the only surprises scientists have seen in recent years. And the cherry on top is the next piece of news from deep space. In 2019, the first image of the boundaries of a supermassive black hole was obtained by the New Horizons telescope. It is known that the object is located 3 million light-years away from us in the giant elliptical galaxy M87. Since the black hole photographs were obtained, scientists have become even more active in conducting research. Can we reconstruct the chronology of events? 92 days after the start of observations, that very sensational, although rather blurry photo of the black hole was captured. But the landmark discoveries don't end there. Astronomers were able to obtain an image of the polarized emission from the accretion disk. After a thorough analysis of the data, researchers gained a clearer understanding of what happens to the magnetic field in the vicinity of the black hole. The information obtained is much more significant than the image of the black hole itself. After all, no one has ever gotten this close to it before. It was this unique data that made it possible to examine the process of accretion of objects in more detail. For example, recently astrophysicists received valuable information from several research groups. The information concerned a powerful jet streaming out from the core of a black hole. Scientists still cannot fully understand the essence of the processes taking place, but this allows them to adjust existing theories. But let's set aside the dry scientific theories. What does this information mean for the average person? It was previously believed that the likelihood of such a huge active black hole forming near the Milky Way was extremely low, but it still happened. Moreover, near M87 there is a distinct energy jet located along the axis of rotation of the black hole. This forces scientists to ask the question, do the properties of black hole magnetic fields differ, or is it all due to an error caused by optical effects that actually turn the unstoppable stream invisible? And that's far from all the amazing discoveries awaiting us as we explore space. Who knows, maybe right now in a neighboring galaxy, there are phenomena occurring that will radically change human life in the future. According to legend, when Albert Einstein met Charlie Chaplin, he said to him, "You will become a great man. In your films, you don't say a word, but the whole world understands you." Chaplin replied, "I admire you even more. No one in the world understands your theory of relativity, but you still became a great man." It is not known for sure whether such a conversation actually took place, but the sentiment makes sense. Einstein's theory of relativity is one of the most far-reaching and complex things ever conceived by the human mind. It provides answers to many of the most important questions about motion, space, and time. But is it perfect? No. There are also paradoxes in the theory of relativity, and one of them is the so-called twin paradox. And to figure it out, we'll have to fly into space and come back. Are you ready? Let's go. So, let's imagine two twins. Let's say their names are Tolya and Kolya. As fate would have it, Tolya became a cosmonaut, and he has to go on a journey to a distant star. Kolya, on the other hand, has to wait for his brother's return on Earth. Both brothers have ultra-precise atomic clocks, which they synchronize before the flight. Any good story needs an unexpected twist, and it really does happen. When Tolya returns to Earth, it turns out that his clock is behind Kolya's clock, and as a result, he is now younger than his twin brother. Amazing! Yes, but only for those who aren't familiar with the theory of relativity. So, how is it even possible that a cosmonaut making an intergalactic flight ages less than his brother who stayed on Earth and ends up younger than him? The thing is, time isn't the same for everyone. It's relative, and it flows differently for those who move at different speeds. The faster an object moves, the slower time passes for it. You can easily feel this relativity, for example, when you're riding on a train, and your train meets another one rushing towards you on the adjacent track. At that moment, you clearly feel that you are standing still and only the other train is moving, and at a tremendous speed. But there are people in the other train too. And for them, it's you who are rushing past with a roar while they are standing still. This is where we come to the twin paradox. Because of relativity, it seems to the astronaut that he is actually standing still, and it's the Earth that's moving away from him. We've seen this more than once in science fiction movies, and that's really how it is. Remember our train? When you're riding in it, you're staying in one place, sitting or lying down. And it's the scenery outside the window that's moving relative to you. You yourself are stationary. So if the astronaut is stationary and the world moves around him, does that mean he should be the one to age? After all, the one who stayed on Earth was moving while the astronaut was stationary. But then when both brothers meet, it will turn out that each of them has become older than the other. But that's absurd. This is exactly what the so-called twin paradox is about, which at one time gave Einstein quite a headache and was actively used by critics of his theory. But is it really a paradox? As we mentioned earlier, one of the main principles of the theory of relativity states that the faster an object moves, the more time slows down for it. And this has been proven many times. Moreover, the experiment with two clocks was actually conducted only on Earth. Atomic clocks placed on board a supersonic airplane showed a tiny delay in time compared to the synchronized clocks that remained on the ground. But on Earth, the delay is negligible and we cannot feel it. He won't be able to end up younger than Kolya, even if he spends years in the sky at supersonic speeds. But what about in space, where we're talking about completely different scales of distance and speed? The twin paradox has several interpretations and explanations. One of them involves the acceleration that a rocket develops in space. One of the brothers, Tolya, experiences acceleration as he travels through vast cosmic distances. And the second brother, Kolya, is in a stationary system, that is, on Earth. At the same time, for each brother, time doesn't flow in any special way. Tolya, while experiencing acceleration, doesn't notice his time slowing down. The brothers can only feel the difference relative to each other. Haven't we confused you too much yet? Wait, this is by no means the only interpretation of the paradox, and there is an opinion that acceleration has nothing to do with it. Let's conduct another thought experiment in the spirit of Einstein. Let's imagine that there are 3 observers in constant motion, and none of them is accelerating. Let's call them A, B, and V. Observer A is at rest on Earth. Observer B is moving toward a distant star at a constant speed, and they can do so without acceleration. Observer V is on the opposite side, and in this case at the same distance from the star as Earth. Observer A sees B moving away and V approaching. But despite the fact that A is firmly standing in the stationary system, B and V are moving relative to each other. All 3 will be moving. How can you equate something stationary and something moving? Here, you can use the relativity equation to get the following formula. The time in motion will be equal to the stationary time divided by gamma. Gamma is widely used in the theory of relativity as an indicator of the speed ratio between 2 observers, and it is always greater than or equal to 1. Using this equation, we will see that the time experienced by 2 moving observers will pass faster than for someone who is on Earth. Here is your mathematical proof of ephemeral matter. But haven't you ever felt this yourself? A person in motion will actually feel that not as much time has passed compared to someone who remained at rest. But how does that happen? It's not about acceleration at all. We've already come to that conclusion through a thought experiment. Returning to our observers, we can take into account that observer A is in a stationary frame of reference, while observers B and B are actually in 2 different frames, B moving away and B approaching. But no matter which observer we put at the center of consideration for each of them, the other 2 will have one moving away and one approaching, meaning they are in 2 different frames of reference at the same time. That's exactly how relativity works. The world looks different for everyone. If we go beyond this scheme and add a 4th observer, G, who watches from the outside at the movement of A, B, and B, then we'll see that for G, observer A still has a single constant speed, while B and B have 2 different speeds, as was already proven by the formula above. But what about acceleration? There was no acceleration in our experiment. Does that mean it doesn't play a significant role? Yes. Only one thing matters. We are comparing the time a person spends in one system with the time spent in 2 systems at the same time. The acceleration that is obviously necessary for a person to travel between stars is an incidental factor here. Only time, distance, and speed matter. So how did you like our little journey into the complex yet very fascinating world of time and space? Perhaps this deep dive raised more questions than it answered, but that's the challenging path of science, and we're happy to be your guides along the way. The speed of light is about 299,792,458 meters per second. That's a pretty precise value, isn't it? But how did we arrive at it? According to Ola Römer's calculations, the speed of light is 220,000 kilometers per second. Half a century later, in 1728, the discovery of aberration allowed James Bradley to confirm the finiteness of the speed of light and refine its estimate. The value obtained by James Bradley was 308,000 kilometers per second. The most accurate measurement of the speed of light was carried out in 1975 based on the standard meter. According to this measurement, the speed of light is 299,792,458 meters per second. You could say that this is the highest speed in the universe, but can we reach it? In theory, to even get close to this speed, our spacecraft would have to have no mass at all. So there's a paradox here. In order to accelerate to the speed of light, you shouldn't physically exist. The speed of light may seem enormous, but when you take into account the distances between cosmic objects, it's not that impressive anymore. Moreover, it seems rather modest compared to human ambitions for fast travel from one point of the universe to another. Of course, light can circle the Earth 7.5 times in 1 second, but even light has its limits. When talking to a person who is 1 meter away from you, you see him 3.3 nanoseconds in the past. Actually, nothing in the universe appears to us in real time, right now. Let's try to start with well-known objects such as the Moon. The natural satellite of our planet is located 380,000 kilometers from its surface. And this means that from Earth we see the Moon as it was 1.3 seconds ago, the Sun as it was 8 minutes ago, and Mars as it was a whole 14 minutes ago. This means that it takes almost 14 minutes for the Mars rovers to make even the simplest movement. After all, they are controlled directly from Earth. It turns out that the speed of light is a kind of limit for any other speed. Radio, microwaves, and gamma waves. Let's try to move even farther. The nearest star system is 4.3 light years away from us, and that's the famous Alpha Centauri. There are 3 stars in the system, and the smallest one, Proxima Centauri, is the closest, at 4.2 light years from the Sun. There is a planet orbiting Proxima Centauri that is close to Earth in size. Let's imagine that it is inhabited by intelligent life forms who, like humans, are interested in observing space. So the aliens would be able to observe Earth as it was 4 years in the past. If their telescope can see every person on Earth, then they would be able to see you as you were 4 years before the moment of observation. The center of our galaxy, the Milky Way, is 25,000 light years away from the Sun, which means we see it as it was 25,000 years ago. Let's zoom in. Let's imagine that there is a planet 2,000 light years away, where there are also intelligent observers. To observe Earth, they would need a telescope several 100,000 kilometers in diameter. We've all seen pictures and videos of the dark, nighttime side of Earth, and clearly remember the clusters of glowing dots, our cities. But 2,000 years ago, there were no megacities, and it would be centuries before artificial light was invented. To see a human, you would need a telescope about 11 billion kilometers in diameter. And that's, mind you, the diameter of the solar system from the Sun to Neptune. But let's imagine that our mysterious neighbors have such technology. They would see ancient Rome and other civilizations from that distant era. By the first year of the Common Era, Rome, whose population was somewhere between 20,000 and 1 million inhabitants, was the largest and most powerful city in the world. Most of what we know about the civilization of that ancient era is known to us from history recorded during Roman rule. The population of the Earth was about 231 million people. The most populated areas on the planet were communities founded near the Ganges, Tigris, Yangtze, Nile, and Po rivers. Do you want to go even further? The closest galaxy to us is Andromeda. It is much larger than our Milky Way and is believed to eventually collide with it. Andromeda is located 2,500,000 light years away from the Sun. We can observe it as it was 2.5 million years ago. An alien observer with telescopes of a colossal diameter of 15 trillion kilometers would not see any intelligent life on Earth at all. Humans are only just emerging as intelligent beings, learning to use tools, and are hardly aware of the great journey that lies ahead of them. It is worth noting that the aliens would be able to see not only the Earth in the past, but the entire Milky Way galaxy, as it was 2.5 million years ago. It's breathtaking to think about such scales, but what if we go even further? The largest spiral galaxy, NGC 6872, is located 212 million light years away from our solar system. The diameter of the telescope would have to be truly fantastic, about 1 quadrillion kilometers or 132 light years. So, what will the observer see this time? Well, first of all, they won't see the familiar outlines of Earth's continents that we're all used to. Instead of them, there was only one supercontinent, Pangaea, which much later would split into Laurasia and Gondwana, separated by the Tethys Ocean. Both supercontinents would later break up into smaller parts, and their collisions would lead to active mountain formation. The result of Africa pressing against Europe will be the Alps, and the collision of India and Asia will create the Himalayas. Secondly, most of the Earth's inhabitants they would be able to see have long been considered extinct. The Jurassic period was the heyday of forests. Abundant rainfall contributed to the spread of flora not only in the ocean, but also on land. Dense forests were mainly represented by true ferns and gymnosperms. The class of gymnosperms called cycads has survived to this day. Today, representatives of Jurassic flora grow in humid equatorial forests. The farther away observers are from us, the deeper into the past of our planet they will be forced to look. As you can imagine, the same applies to us if we want to observe them. Voyager 1, a spacecraft carrying a golden record with a message for extraterrestrial life, will help us grasp the enormity of all these scales. It contains greetings in 55 languages, human voices, classical music and sounds of nature, as well as photographs of people and Earth. The record contains the coordinates of Earth and the solar system, as well as diagrams of hydrogen atom emissions. In September 2013, NASA announced that Voyager 1 had crossed the boundary of the solar system. It became the first spacecraft to enter interstellar space. To this day, the spacecraft is more than 20 billion kilometers away from Earth. According to scientists' calculations, the fuel should last for another 10 years of operation, and after that, contact with Earth will be lost. But let's imagine that the fuel lasts for an infinitely long period of time, and Voyager 1 itself is heading straight toward Proxima Centauri. This journey would take 40,000 years, considering that the spacecraft is not moving at the speed of light, but only at a speed of 17 kilometers per second, or in other words, 60,000 kilometers per hour. The scale of space can truly be astonishing, and even though the darkness of the unknown cosmos can be frightening, humanity must fearlessly seek ways to accelerate its spacecraft. Of course, if we tie our future to the exploration of other worlds. When faced with this cosmic vastness, a person realizes how little he knows about the world around him, how much remains unexplored, and how much is yet to be discovered. Why do the laws of the universe work this way and not some other way? Why does the very fact that we have senses seem like a mockery in the face of the distances possible in space? Of course, you can live without thinking about all of this. The world becomes understandable and orderly. But as soon as you start thinking about the incredible phenomena happening around us and far beyond the Earth, the familiar walls collapse and we step beyond the ordinary. Everyone knows that the speed of light in a vacuum is the maximum speed anything can travel in the universe. This speed is almost 300,000 kilometers per second, and that's exactly how fast light particles, photons, travel. Nothing in our universe can move faster than light, because that would contradict not only the theory of relativity, but also the very laws of time. For an object that reached a speed higher than the speed of light, time would literally start running backwards. But what if I told you that there are hypothetical particles whose speed not only exceeds the speed of light, but for which time, literally speaking, flows backwards? Moreover, their existence actually fits within the special theory of relativity rather than contradicting it. How can that be? We'll find out today. So we're going to talk about tachyons, hypothetical particles that have the ability to travel faster than the speed of light. The very possibility of the existence of such particles was first proposed by Robert Ehrlich and Arnold Sommerfeld independently of each other. The term tachyon itself comes from the Greek language, where tachi means fast, and it was proposed by Gerald Feinberg in 1967. The theory about tachyons has its own terminology. For example, particles that move at speeds lower than the speed of light, that is, all particles in our universe except photons, are called tardions. Photons in this theory are called luxons. So where did the hypothesis that tachyons might exist come from? The thing is, in natural sciences, people often reason from the opposite assumption. Is it possible to prove that tachyons don't exist? No. But how can they exist if it contradicts the theory of relativity and plain common sense? As we know, objects that have mass cannot move at the speed of light. Why does this happen? Do you remember the famous formula? E equals m times c squared? This formula from the theory of relativity connects the energy required for motion with the mass and speed of an object. Therefore, for something with mass to reach the speed of light, the energy required would have to approach infinity, which would create a lot of paradoxes. The only particles in the universe that can travel at the speed of light are, of course, light itself, whose photons have no mass. But how can tachyons, even hypothetically, exceed the speed of light if the maximum speed in the universe is only reached by particles that have no mass? If photons have zero mass, does that mean tachyons have negative mass? It sounds unbelievable, but that's exactly the direction scientists are thinking in. They suggested that tachyons might have what's called imaginary mass. What does that mean? Literally, imaginary mass is the degree or measure of how much matter slows down, not acceleration as we're used to thinking. To travel faster than the speed of light, you need to introduce the concept of negative inertia. This is where the tachyon comes in with its imaginary mass. This mass doesn't slow the particle down, but rather accelerates it, so the tachyon's faster than light speed can be partially explained by its imaginary mass. The oddities of tachyons don't end there. If ordinary normal particles accelerate when they gain energy and slow down when they lose it, with tachyons it's the opposite. They should slow down as they gain energy and speed up as they lose it. This leads to the problem of charged tachyons, because charged particles moving at superluminal speeds release energy in the form of Cherenkov radiation. It is also called the Cherenkov effect, otherwise known as Vavilov-Cherenkov radiation. As they gain energy, tachyons will lose energy even in a vacuum, and will move faster and faster, reaching speeds beyond any analysis, let alone visual observation. Simply put, when a tachyon flies through matter, it loses energy because it collides with atoms. But as it loses energy, it accelerates, which makes the collisions even stronger and happen more often. In theory, these collisions should cause further energy loss, and consequently, further acceleration. A vicious cycle occurs, and the tachyon naturally accelerates to infinite speed on its own. It's practically a perpetual motion machine inside the particle itself. Do you think that's the end of the list of incredible things about tachyons? Not even close. In 1970, astrophysicist Gregory Benford and his colleagues pointed out that the existence of tachyons is a direct path to acknowledging the existence of a time paradox. This is related to the possibility of these particles sending information into the past. The very idea of sending messages back in time appeared in physics as early as 1907, when Albert Einstein proposed the theory that if you exceed the speed of light, you could send a message into the past. But Benford developed this theory using tachyons and presented it to the public as a playful story about Alice and Bob. Let's suppose Alice and Bob made an agreement. Alice will send Bob a message at 3 o'clock if she doesn't receive a message from him at 1 o'clock. After receiving a message from Alice at 2 o'clock, Bob immediately sends Alice a message into the past so that she receives it at 1 o'clock. But the second exchange of messages will only take place if the first exchange does not happen. Gregory Benford called the hypothetical communication device between Alice and Bob a tachyonic anti-telephone. If the existence of tachyons is proven, can you imagine what incredible possibilities this will open up for humanity? Tachyons are common in science fiction. In the immortal science fiction novel Dune by Frank Herbert, there is a tachyon network that allows for instant communication and even control of particles in the universe. Tachyons play a major role in the plot of the television epic Star Trek. If we leave science fiction aside, at the moment some physicists believe that tachyons may have existed at the time of the Big Bang, violating causality, but now they no longer exist. Moreover, tachyons may be directly connected to the Big Bang itself and to the very possibility that it happened. But how? There is a theory that before the Big Bang, the universe existed in a state of false vacuum where tachyons were present. But their presence meant that this was not the lowest energy state of the system, and therefore the system was unstable. At some moment, a tiny gap appeared in the fabric of space-time, representing the true vacuum. The gap began to grow, and a bubble appeared. Outside the bubble, tachyons still existed, but inside it, there were none. As the bubble grew, the universe we know appeared, a universe without tachyons. That was the Big Bang. So tachyons can exist, but somewhere outside our universe? Who knows? The search for these mysterious particles has never stopped, but so far, they haven't yielded any positive results. In 2011, when scientists from CERN conducted an experiment called OPERA, related to the study of neutrino oscillations, it seemed that the answer was very close. During the experiment, something incredible happened. The scientists claimed that they had discovered particles traveling faster than the speed of light. However, unfortunately, it soon turned out that the mysterious particles were not tachyons at all, but merely the result of inaccuracies and errors in the synchronization system. So, does the most mysterious of all particles really exist in nature? Will we be able to get an answer to this question in the near future? Anything is possible. Science is advancing by leaps and bounds, and much of what was once only hypothetical and seemed like science fiction has eventually been proven and become an undeniable fact. One thing can be said for sure: the possibility of discovering tachyons, and most importantly, finding a way to interact with these particles, is the path to that very future that, for now, we can only read about in science fiction novels. What do you think? What kind of budget would you need to become the first space tourist on Mars? $10 billion. According to Elon Musk, with this amount, you could easily leave our vast planet behind. But did you know that you have the opportunity to see the beauty of Mars and hear what it sounds like without leaving Earth? In recent years, humanity has made great strides forward. On March 17, NASA released an audio recording made on March 7 using a microphone installed on the rover, and it lasts a full 16 minutes. We have already heard the sound of the Martian wind, and now we can analyze the noise made by the rover itself as it moves across Mars, where it traveled just over 27 meters. And this is really very interesting because in addition to the creaking of the rover's tracks, the recording also captured some rather curious knocks and taps. On the SoundCloud website, there are two versions of the recording, the full one and a 90-second cut, in which extraneous noises have been suppressed using filters. Listen for yourself. What do these sounds make you think of? Here we hear the Mars rover starting to move, followed by metallic tapping sounds. The tapping can also be heard in other parts of the recording. And in some places you can hear a real rumble. Doesn't it sound like Martians attacked Perseverance and are trying to break into it? But everything is explained much more simply. Many people, when they see a picture of the Mars rover, don't realize that the wheels are made of metal. When you drive on these wheels over rocks, it's actually very noisy, said Vandy Verma, senior engineer at NASA in Southern California and driver of Perseverance. Why are the recordings from Perseverance so important to us? Perseverance is the first Mars rover that managed to successfully record and transmit audio from Mars, since previous attempts had failed. Microphones were installed on the Mars Polar Lander rover, which crashed during landing on the surface of Mars, as well as on the Phoenix lander, which, despite a successful landing, was unable to make recordings due to electronic problems. But that's not all. The rover's cameras also captured a real Martian dust vortex, which is also called a dust devil. We don't know its speed or height, but it's known that dust devils on Mars can reach up to 8 kilometers in height. The mechanics of their formation are the same as on Earth, and they consist of the interaction between the sun-heated surface and the cold and hot air currents above it. From space, such whirlwinds look like this. Impressive, isn't it? What do you think? Could such natural phenomena on Mars hinder future colonization? Write your opinion in the comments. But let's get back to Perseverance. Perseverance is already making real breakthroughs, far surpassing its predecessors. And who knows what we will see and hear when the cameras on the Ingenuity drone turn on. It's still charging, but it'll begin flying over Mars very young. To be continued. The more videos about space I create, the more I'm amazed by the complexity and mystery of the laws. Tell me, what do you think? Can we look beyond the horizon? Of course. After all, if we just move a little forward, we'll see what's hidden beyond it. And on the Little Prince's planet, it's even easier to do that. If you want to see a sunset on asteroid B612, you can watch it several dozen times a day. All you have to do is move your chair closer to the horizon. But the phenomenon we're about to discuss isn't something that can be easily overcome. Or rather, it's impossible to overcome it. We're going to talk about the event horizon of a black hole. Let's start with the terminology. What is the event horizon? It's a three-dimensional hypersurface that encloses the area around the cosmic monster. This imaginary line can rightfully be called the point of no return or a one-way ticket, because everything that lies beyond this boundary is lost to the observer forever, even superfast photons of light. An object or living being that gets caught in this hellish vortex will sooner or later reach the singularity at the very center of the black hole. But by the time it reaches its final destination, the object is unlikely to remain intact. Before that, it will be torn apart by an incredible gravitational force unmatched anywhere else in the universe. Why do we think there's a singularity there? After all, we don't really know for sure what's inside a black hole. Information about this is classified by nature itself and protected by barriers of relentless laws of physics. But humanity continues to speculate, and a journey beyond the event horizon and back would help confirm these guesses. Is this possible? Let's start by finding out where black holes come from. Astrophysicists know this for sure. Massive formations eventually turn into massive stars, which live a life that's too fast by cosmic standards. Who can be considered real candidates to become future black holes? This star burns its fuel over tens of millions, not billions, of years and combines several hundred solar masses. When the hydrogen supply runs out, megatons of stellar matter, under the influence of hellish gravity, instantly collapse. These stars produce unimaginable bursts and shrink so much that the particles making up the former stars literally merge into each other. Some of them become neutron stars, but especially dense and massive objects turn into the invisible monsters of the universe. They are so massive that they literally collapse through the fabric of space, creating a depression or a funnel. Theoretically, any object can become a black hole, even the sun or the Earth. For example, in order for our planet to turn into an invisible magnet, its radius, while keeping its mass the same, would have to be 1 centimeter, and for the sun, this value would be 3 kilometers. The critical compression of a body is called the Schwarzschild radius. And now, returning to the question asked at the beginning of the video, let's ask once again, is it possible to escape the inhospitable embrace of black holes? Physics is unwavering on this question. To break away from any body, you need to reach escape velocity. For Earth, that's 11 kilometers per second. For the Sun, it's 617.7 kilometers per second. For a black hole, the escape velocity exceeds the speed of light. And as we know, it's impossible to reach that. So is that the end of the discussion? Since it's impossible to escape the event horizon, that should settle it. But we're persistent people, so we'll try to dig a little deeper. What if we tried tying some object to the ship with an incredibly strong cable and lower it into the pitch black darkness of the black hole? Or use an elevator for this purpose? Is it possible to pull the object back, like a ship's sounding line from the depths of the ocean? It would seem there's nothing special about it. It'll plunge in, explore the vastness of the cosmic trap, and finally satisfy humanity's intense curiosity. We have to disappoint you, but not in this universe. The most likely scenario in such a situation is gradual spaghettification, with not only the object attached to the cable, but the ship itself being dragged into the darkness of the hole. And all of this will inevitably rush toward the Holy of Holies, the singularity, the point where everything begins and ends. The size of the funnel doesn't matter. The no-return rule is the same for every kind of black hole. And what will happen if a person standing right at the edge of the event horizon tries to dip just a hand or a leg into the terrifying funnel? You could pull it back instantly, right? Absolutely not. As I said before, anything that falls into the clutches of the hole never comes back. All that's left is to hope for the mercy of a nearby astronaut who will cut off the limb of the brave soul before they're completely sucked in. But what about the optimistic statement by Stephen Hawking, who urged us not to give up, claiming that even from this cosmic coffin, there is a way out? It exists, just not in the way you'd want. A fact that might slightly comfort a traveler who falls into a black hole is that it isn't eternal thanks to quantum physics. The lifespan of this deadly object is enormous, but everything comes to an end eventually. However, it should be noted that the event horizon will exist until the very last milliseconds of the black hole's life, right up to the moment when its mass becomes zero. And this is when liberation will come. Stephen Hawking claimed that in the final hours of a black hole's decay, the funnel gets rid of excess information. It spits out jewels in the form of radiation, and the power of the cosmic monster's death cry can reach up to 5 million megatons in TNT equivalent. The information the hole emits in its death throes also includes information about the bodies that once fell into the monster's belly. This is similar to the urns in the columbarium. The ashes retain fragments of information about the person who was burned, but they're of no further use. Although, from a physics standpoint, this extravagant explanation resolves the paradox of energy transformation and its immortality. It's a pity that there will be no one to witness such an impressive event, because by that time there won't be a single star or any other source of light left in the universe. If any of us could witness the death of the last black hole, the sight would be overwhelming. Amidst the pitch darkness and emptiness lasting 10 to the power of 100 years, there would suddenly be a dazzling flash, the last ray of light in the cosmos. And then, the silent explosion of the black trap would finally release those who once recklessly fell into its grasp. Thus, there is a way out of the embrace of a black hole, but information about it is of little practical use to us. Although it does make for vivid and interesting mental images. The conclusion is obvious. Until humanity has armed itself with sufficient knowledge and improved technology, it's better not to approach black holes, but to admire these frightening objects from afar through the eyepieces of telescopes. The universe is damn treacherous. Every time these guys get even an inch closer to understanding its laws, the universe immediately throws them back about 30 meters, presenting yet another surprise. After all, we humans have always dreamed of studying something new, something unexplored. We are used to perceiving its meaning on a microscopic scale. But what if we look at the problem a little more broadly? What if everything we've seen has already happened before? What fate awaits humanity if the universe suddenly dies? Will anything remain in its place? Or will the world be consumed by dead emptiness? The greatest minds of humanity have pondered this throughout different eras. At the end of the 19th century, Friedrich Nietzsche, known for his unconventional view of existence, once came to a strange conclusion while walking in a garden. Infinity is quite fruitful. It has unlimited time, so eternity is capable of producing countless repetitions. Beings, events, phenomena. According to the flamboyant philosopher, infinity can even create clones of human consciousness. This idea was later enthusiastically supported by the physicist Ludwig Boltzmann. Let's pause our tangled thoughts for a moment. let's set aside philosophical speculations and turn to the question of the final point of existence, toward which our macroscopic world is gradually, albeit very slowly, moving. What's the point of talking about rebirth if in the end, everything will perish and turn into emptiness? But there's no need to despair in advance. Perhaps emptiness is not the end at all, but only the beginning. No matter how hard science fiction writers try to convince us otherwise, the Earth and the surrounding cosmos do not seem like the product of someone's dream. Everything seems quite real and tangible. Moreover, it's quite orderly. Think about how precise and meticulously calculated the stages of the universe's development are, starting from the initial singularity, the origin, inflation, gradual cooling, formation of the first protons, neutrons, and atomic nuclei, appearance of molecular clouds, birth of the first stars, death of aging stars, filling space with the necessary elements, emergence of a new generation of stars and solid planets, birth of galactic clusters. In one of them, called the Milky Way, the solar system formed, where a solid celestial body of the right shape, weight, and size formed, with the necessary rotation parameters and the perfect distance from its star. In short, all the conditions appeared for the seeds of life to grow and flourish abundantly on this planet. The probability of humanity appearing is extremely small, but nature took advantage of it. And now, you are watching this video thinking about your upcoming date or discussing a book you've read over a cup of coffee. The universe has been moving toward this moment for almost 14 billion years, surviving countless risks and taking advantage of every favorable chance. And all of this just to one day simply sink into empty nothingness. Whenever you feel like mourning the fact that in billions of years, mountains, seas, people, stars, and even black holes will disappear without a trace, remember an undeniable truth. All of this is just a collection of particles that have come together to form the shapes of the objects we observe. And just like a pile of Lego bricks poured out of a bag by a restless child, they can come together from chaos again into something similar, as well as into a multitude of different forms. And now let's get back to Ludwig Boltzmann and his theory. The point of it is that any closed system tends to gradually increase in disorder, that is, to develop chaos and entropy, moving away from ideal conditions toward real ones. But then why does the universe look so well thought out? Boltzmann answered this question as follows. The world as a whole is nothing more than a fluctuation, a randomly stacked pile of books in the chaos of a library. So, does that mean chaos is capable of producing something worthwhile out of absolute disorder? Right after this theory emerged, no one took it seriously. And only decades later did the law of quantum vacuum fluctuations appear. It follows from this that no void can become so sterile that it won't eventually gather a group of particles. The universe has eternity at its disposal, and during that time, atoms will have enough time to visit every cell of the vacuum multiple times. Millions of times, they will form different algorithms and structures. And in the end, it's possible that analogs of the Milky Way galaxy, the planet Earth, clones of people, objects, and basically anything or anyone could appear. So was Nietzsche wandering among the cherry trees actually close to the truth? A particularly interesting subject which has sparked discussions in the context of such reasoning is the Boltzmann brain. The question has often been raised, would consciousness be authentic if we tried to upload it onto some kind of digital medium? Even this is something we are not able to answer yet. But for an organized bundle of neurons to form out of the emptiness of a vacuum, even over millions of years, that seems like complete nonsense. A Boltzmann brain is a hypothetically possible object. It is the product of a collection of particles that have come together over billions of years. Moreover, this autonomous formation is capable of being aware of its own existence. It's hard to believe, but from a scientific point of view, the emergence of such an intelligent conglomeration is more likely than the appearance of a human being through a long process of evolution. Moreover, it's possible that your seemingly unique consciousness is just a copy that has arisen in the universe hundreds of billions of times. Therefore, considering the age of the universe and the total lack of understanding of its laws, it's at least presumptuous to consider yourself the original. An object like a Boltzmann brain could theoretically appear in a de Sitter vacuum once every 10 to the power of 10 to the power of 50 years. It is precisely Willem de Sitter's model that features a vacuum that isn't empty, but filled with many particles. So forget about emptiness. For those who do not want to be a shameful copy, but demand to be elevated to the status of an original, a theory was invented to counter the previous one. When our world enters the era of eternal darkness, the vacuum will undergo premature decay, and the Boltzmann brain simply won't have time to form. If we stop indulging ourselves with the illusion of our own uniqueness and try to look at the problem of existence from a different angle, then the idea of the Boltzmann brain pushes humanity into the abyss of solipsism. This is extreme subjective idealism, whose adherents are convinced that only consciousness is real. Everything else is merely its creation. Be that as it may, no one really knows for sure, but the possibility that after the death of our world, everything will repeat itself many times in different combinations, rather than disappear forever, gives hope. And this fact gives hope no matter how the universe ends. Whether it's a collision with a neighboring world just as vast, the scenario of heat death, or the case of the Big Rip, a gradual decay into particles. The theory of continuous cloning only fails if our universe is a computer simulation. Nothing prevents its creator from disconnecting us from the network forever. After all, people sometimes log out of their gaming accounts in GTA San Andreas, Dota, or Stalker. But these are just empty fantasies, like something from Ren TV, right? But the Hubble channel both believes and questions everything at once. We are open to discussing any issue and we respect your opinion. Come in, join the discussion, and by the number of likes, it's easy to tell whether the topics covered on the channel are too boring or not. The universe is complex and multifaceted. There are many things in it that are hard to understand, and sometimes even downright meaningless. Or at least they seem that way to someone who isn't familiar with them. Today we're going to talk about numbers, but not the usual ones we're used to. Almost impossible numbers. Mathematics is a science that doesn't tolerate approximation, but at the same time within its framework, both the irrational number pi and the infinity symbol coexist. Besides the well-known, though huge numbers, there is one that defies human imagination. Why? Is human imagination really that limited? By no means. It's simply impossible to visualize this number. The number, which once made it into the Guinness Book of Records, is named after the mathematician Ronald Graham. The world learned about it in 1977 when the scientists came up with a non-trivial solution to a complex problem in the field of combinatorics involving a hypercube. The collection of digits presented as proof of Ramsey theory turned out to be the upper limit of numbers ever used in mathematical examples. But the point of the numbers is not to write them down until your hand gets tired. Their value should correspond to some quantity. Some sets are really huge, but none of them can compare to Graham's number, abstract and relentless. Before talking about it in more detail, it's worth briefly mentioning the quantities the human imagination can still grasp. The huge numbers given below are not just a random collection of symbols. They correspond to a specific group or area. As a rule, they are presented in the form of numbers raised to a certain power. This method is concise and easy to understand and write. Let's start by mentioning millions and billions, which almost everyone is familiar with. For example, who wouldn't want to hit $1 million jackpot? Who doesn't know the Earth has 7 billion people? Everyone has heard at some point about the 100 billion stars shining in the Milky Way? Or about the same number of neurons in the human brain? It's relatively easy to imagine a quantitative picture involving a million or even a billion. They are often written as a number with an exponent, 10 to the power of 6 and 10 to the power of 9. Next come tens with higher exponents. 10 to the 12th is a trillion, 10 to the 15th is a quadrillion, 10 to the 18th is a quintillion. But even these huge numbers have real-world equivalents. For example, a trillion fish live in Earth's oceans, which contain about a quintillion cubic meters of water, and along the shores a quadrillion hardworking ants crawl. But that's just a warm-up. Now the real craziness is about to start. Universal sextillion, 10 sextillion, universal 10 to the 21st power, is the approximate number of stars in the observable universe. In any case, astronomers settled on this number, agreeing that it's the minimum. No one has ever counted the stars by hand. A sextillion is a 1 followed by 21 zeros. Of all the really large numbers that have a real-world equivalent, this is the smallest. Earth's septillion. That's 10 to the 24th power. We rarely hear or use this word in speech, but nevertheless it's worth remembering. A septillion grams is the weight of our planet. A tongue twister number, 100 quinvigintillion, is 10 to the 80th power. It's comparable to the total number of subatomic particles in the universe. The legendary Google. A number, named by mistake, revolutionized humanity's thinking and worldview. A 1, followed by 100 zeros, became the stuff of legend, and its creator couldn't find a suitable technical use for this numerical monstrosity for a long time. Finally, a theory was developed stating that after 10 to the power of 100 to the power of 100 years, the last black hole will explode, and the universe will begin a countdown, gradually contracting into the point from which it was once born. A visit to Planck. As a result, to the power of 185, the volume of the observable universe from the perspective of Planck's units. This is the smallest size that a person is able to imagine and calculate. The same can be said about the number itself. That's where our imagination reaches its limits. But let's test it once more anyway. Strings of worlds. 10 to the power of 10 to the power of 500 is the number of possible universes if we are to believe the intricate and hard to understand string theory. From here on, it's all dense material and topic rabbit holes. It's a realm of numerical monsters that make you want to exclaim, they're just mocking us. And yet there are numbers much larger than the ones we've mentioned. At the same time, despite being extremely abstract values, they actually represent something. Except perhaps for Googleplex. It's just a nice and widely publicized number, 10 to the power of Google. For example, the huge but useful Mersenne number, the current Mersenne. Their limit is known. The largest prime number, which is divisible only by 1 and itself. It is 2 to the power of 43,112,609 minus 1. That's almost 13 million digits. Can you imagine something like that? Or an even more intimidating digital titan, the skews number. It represents the upper limit for a mathematical problem and is equal to 10 to the power of 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 963. And compared to it, even Googleplex is trailing far behind. And now finally we've come to the true mathematical monster, Graham's number. This is the unbreakable boundary of possible solutions to that very hypercube problem that was mentioned at the beginning of the video. To explain how it came about, we need to recall Knuth's up arrow notation, which is used to write very large numbers. The essence of the method is to add vertical arrows instead of using stacked exponents. For example, 3 up arrow 3 is 3 to the power of 3. So 1 arrow means exponentiation. Next, when you add another 3, 2 arrows. 3, the expression will look like this. 3 to the power of 3 to the power of 3, or 3 to the 27th power. That's about 7 trillion, or 3 to the 27th power, or 7 trillion, 625 billion, 597 million, 484,987. That's not that much, you might say. Wait, soon there will be 100 times more. For example, 3 arrows 3, or G1, forms a tower of threes that's 7 trillion high. If you stretch it out in space, this path would easily reach Mars. And note, this isn't the number itself, just the stack of exponents. Just 5 threes from this tower completely cover Googleplex, and the first 10 centimeters of this monstrous stack stump all existing computers on Earth. Beyond that, there is emptiness and ignorance. That's something we have to live with now. The arrows increase to 100 or more. The tower of exponents grows, but it's still G1. Then comes G2, where the number of Knuth's arrows will be equal to the number G1, and so on layer by layer. Each previous layer is numerically equal to the number of arrows in the next one. Graham's number contains 64 of these G's. If you're expecting to see another septillion sextillions as a result, you'll be disappointed. This monster doesn't have a numerical representation. It's represented using a formula. G equals F to the 64th power of 4, where F of n is 3, with n up arrows 3. There's no point in calculating all of this, and it's not safe either. You might end up in a mental hospital like the geographer from the Golden Calf. To help you understand, we'll use an analogy, but it's better not to imagine it too vividly either. Graham's number wouldn't fit into those 10 to the 500th power multiverses, even if you numbered every single particle. Sometimes it seems that this numerical madness leads more into the abyss of philosophy than mathematics. As if it's a separate matrix where numbers exist independently of us, beyond human understanding. But this mathematical nightmare does have an ending. Here are the last 10 digits of the mind-boggling number: 24, 64, 24, 64, 19, 53, 87. Remember and share them. They could reach your grandchildren. Let's reveal the secret. Even Graham doesn't know the first one. If you still decide to calculate the first digits, keep in mind, you probably won't make it, because the calculation will be interrupted almost at the very beginning by the collapse of the universe. After everything you've heard, many of you will have a question. Who needs this? Why calculate the upper limit of variability of colored segments of a mythical hypercube? But don't jump to conclusions. What seems impossible or even absurd now may become elementary and quite real in 1,000 or 10,000 years, just like cars and airplanes, which were hard to believe in just a century ago. Energy is the key to everything. This fact has been unshakable since the time of Prometheus, with his divine gift of fire, which we now use to boil water, cook food, and heat our homes. By tracing the energy transformations of humanity, one can notice that gradually, members of the Homo sapiens species moved from using muscle power to employing mechanical devices. They harnessed the forces of water and wind, and primitive campfires were replaced by nuclear power. The mastery of new energy sources and the increase in the amount of energy allowed people on Earth to develop continuously. and only the sun is still beyond human control. The giant furnace could give us immeasurably more, but people use only a small fraction of the star's energy. A megastructure proposed by Freeman Dyson and named after him would help accumulate it completely. Until recently, the Dyson sphere was considered a fantastic project, but modern scientists have developed several potentially feasible designs for a structure that captures solar energy. Moreover, due to the obvious benefits of building a sphere, astrophysicists believe that such structures have long filled the universe. We just aren't able to detect them yet. The appearance of a Dyson sphere near the sun would automatically upgrade our civilization to level 2 on the Kardashev scale. Humanity will earn the right to receive this rank if it fully utilizes the energy of its parent star. Of course, we're skipping steps, since at the moment we haven't even reached a Type 1 civilization, which fully harnesses the energy resources of its own planet. But still, right now we are closer to understanding the significance of the Dyson structure than ever before. So, what does terrestrial astroengineering propose in terms of building a sphere? 3 simple questions need to be answered. What will the structure look like? What materials will it be made of, and where should it be built? The last question is the easiest to answer. It needs to be placed at a certain distance around the sun. If we consider an uninhabited version of the sphere, it makes more sense to place it closer to the parent star. However, the following problems arise. How do you overcome the monstrous gravity of the sun? How do you protect the structure from the sun's energy onslaught? How do you shield the sphere from damage from coronal mass ejections? To solve these issues, it is necessary to select ultra-strong yet lightweight materials, as well as provide an unprecedented cooling system. The most optimal location for the sphere is inside Mercury's orbit, which means in this case its radius would be about 23 million kilometers. At such a distance, the structure will not collapse onto the surface of the star, and with proper assembly, it will collect the maximum amount of energy. But this scheme has drawbacks. If you make the megastructure solid, it will disrupt the stability of the planets in the solar system, and this will threaten the very existence of life. This leads to the second question. What should the design of the structure be? Obviously, building a solid sphere in close proximity to a star is only possible if it's someone else's system. You should create something different in your own system. For example, a structure consisting of many modules connected by a common communication network, but not physically linked, each one on its own orbit. This lighter version is called a Dyson swarm and is seen by scientists as the most likely option. The system will involve trillions of mirrors focusing sunlight at the network's nodes. The next problem? Where do we get that much material? If we build the sphere within Mercury's orbit, then by conservative estimates, we would need an amount of material equal in mass to Jupiter. If we place the ring just beyond Earth's orbit, like in Larry Niven's novel, humanity will quickly hit a dead end. There won't be enough material, even if we dismantle all the planets in the solar system. So where do we get that much raw material? The first candidate for gradual industrial dismantling is boiling mercury. For example, you can extract hematite from its core and create polished mirror modules. Robots will dismantle the first planet of the solar system in about half a century. And don't think that this is such an impossible task. Turning a celestial body into mountains of mineral resources is just like dismantling a house, brick by brick. Only the process will take hundreds of times longer. What will the modules of the Dyson swarm be made of? Most likely from durable foil, titanium and steel tubes, fiberglass panels, and hematite mirrors. Next comes the question of the nuances of modifying the astroengineering structure. On Mercury, it will be necessary to place a 3D printer to create individual parts near the solar sphere and deploy powerful drilling rigs. The process definitely needs to be coordinated remotely and be fully automated. This will simplify and reduce the cost of manufacturing spare parts, creating infrastructure facilities, and transporting elements into orbit. Each module of the swarm must be self-coordinating, possess complete autonomy, and be able to fix possible malfunctions on its own. How do you deliver structural parts into orbit? You can use a rocket tug or an electromagnetic railgun, from which the structural elements will be launched as if from a slingshot, and then unfold in place like giant kites. The fact that Mercury has low gravity is a huge advantage because it's easier to launch modules into the desired orbit from its surface. It all seems to add up, but after thinking about it, you realize the main problem hasn't been solved. And what is it? You might laugh, but once again, it's an energy problem. To implement this project, we need as much energy as the Dyson sphere itself would provide. Solar panels placed near Mercury will help partially solve this dilemma. And later, the parts of the Titanic swarm launched into orbit will begin to perform accumulating functions, multiply themselves, and construction will speed up. If it takes about a month to build a square kilometer of panel, then quintillions of cells will surround our star in just a decade. It's hard to overstate the Dyson swarm's significance. The project opens up possibilities for our civilization that we can't even imagine. They will establish habitable colonies, set up refueling stations, and set up industrial sites on the artificial sphere. With the help of modules, concentrated beams can be directed at any object, whether it's an asteroid that needs to be vaporized or a space shuttle that needs a boost. In addition, the structure can be endlessly upgraded and improved by adding new functions. The swarm's elements are like a titanic transformer. They can be reworked in any way, even to the point of creating an arc ship for intergalactic travel based on the sphere. The construction of the pyramids in Giza is just like making sandcastles in a sandbox compared to building a Dyson swarm. The implementation of the project from start to finish will take hundreds of years, but it's worth it. Perhaps our descendants will be passionately working on building the structure. In the meantime, the Hubble channel invites viewers to imagine the incredible scale of the structure and be amazed by the power of the human mind. Sometimes unexpected questions come to people's minds. While a child is growing up, they are interested in questions that later seem simple. Why does a butterfly fly? Why do leaves fall? And what makes the sun shine? But adults have trickier questions. It's not enough for them to just know and be happy that a star warms the Earth. Adults want scientific proof of the process. And then, an unstoppable imagination starts to paint incredible scenarios and demands that they be brought to life. For example, some people seriously wonder what would happen if the sun were blown up. And is it possible in any way to put it out? Let's skip the question of whether this action makes sense and say right away, not with our abilities. In other words, human civilization has not yet reached the level where it would be able to control the life of its own star as it pleases. And at this stage, that's a good thing. We don't let little children play with matches. But no one stops us from thinking about this topic. Moreover, some scientists have asked similar questions at different times. Our sun is a yellow dwarf, a main sequence star, and a relatively stable celestial body with an average lifespan of 10 billion years. Without this modest star by universal standards, the existence of a habitable Earth would be unthinkable. Accordingly, provoking the explosion of the sun would be extremely reckless. And besides, how can you blow up something that has been in a state of constant detonation for the last 5 billion years? German astrophysicists from the Max Planck Society tried to find out 12 years ago why some stars explode instead of simply fading out on their own. To do this, they used a powerful computer for modeling and systematized observational data related to the appearance of supernovae. When Ewald Müller and Wolfgang Hilbrand tried to understand why a colossal explosion occurs, igniting the bright beacons of supernovae, explaining it proved very difficult. Computer modeling of the detonation process, instead of the actual explosion, showed that the star activated a self-regulating mechanism, allowing it not to explode, but to quietly fade away. Later, when additional factors that had not been considered before were added, the process, although simplified, was still examined in detail. One thing became clear. No matter what type of star explodes, something has to trigger the detonation. Approaching critical mass, uncontrolled nuclear reactions, a sudden drop in gas accretion, instant core collapse, or all of the above together. So how can humanity influence the sun? At this point, it's almost laughable to even talk about it. If you look through the planet's nuclear arsenal, it's easy to find out that the most powerful thing we can offer the sun is hydrogen warheads. Let's suppose that our ships somehow manage to deliver several Tsar bombs with a yield of 50 megatons each to the surface of the sun. They would need to get past its corona, which can reach 1,000,000 degrees Celsius. What could these weak explosions do for us? Considering that the sun regularly experiences up to 20 plasma eruptions a day with a combined power of over 1 billion megatons, anything we do from Earth would be like an ant crawling on the back of an elephant. But what if we do it differently? Since we've safely passed through the deadly solar corona, maybe we could dare to plant a detonator inside the sun itself? And another miss? If the impossible scenario comes true, the sun's stabilizing mechanism won't allow even the slightest malfunction. When something like this happens for natural reasons, the star immediately activates thermoregulation and the situation normalizes instantly. Otherwise, the sun couldn't have lasted 5 billion years. The same would happen if Earth's bombs were detonated. Our star, an amazing creation of the cosmos, without which life on Earth would be impossible. That's why the very idea of its destruction is absurd. Besides, it's laughable. After all, we have nothing that can stand against a gigantic torch with a diameter of 1,392,000 kilometers, burning 700 billion tons of hydrogen every second. With such an active loss of matter, the sun should have burned out long ago. But some process has been keeping this giant furnace running for a long time. What is it? These are thermonuclear reactions occurring in the core of the star, constantly supplying it with energy. So, are we actually considering detonating a bomb on the surface of a bomb? Nonsense, isn't it? But detonation isn't the only option for destroying a star. What if we use other methods and extinguish the sun forever? Basically, for our star to go out, we either need to cool it down or stop the thermonuclear reactions in its core. The second will happen on its own in about 4 to 5 billion years, when the process of turning hydrogen into helium stops. But as for cooling the sun, we could try to do that by artificially expanding its surface area, for example, by bringing a neutron star neighbor closer to our star. Then the sun would have to share its matter with it, and it would gradually turn into a dim white dwarf. There's another extravagant way. Try to spray the sun with a gigantic fire hose. Although this is not just fantastical, but also completely useless. The water would simply evaporate without a trace in the corona, never even reaching the star. After all, no one in their right mind would water the Satan missile complex with a garden watering can. But it turns out that we weren't the only ones to come up with such a crazy idea. Astrophysicists examined this idea thoroughly and revealed their findings. If you pour onto a star a volume of water equivalent to 70 times the mass of the sun, the effect will be the exact opposite. The star not only won't go out, since the processes happening on it are not the same as those that sustain fire on Earth, but it will burn even brighter, increasing its size by 1/3 and its brightness 6-fold. Truly, that's a case of getting exactly what you asked for. And for dessert, here's one more method. Let's move away from explosions and cooling and turn our attention to the collision of the sun with large celestial bodies. In our system, the most likely candidate is Jupiter. Compared to the sun, it is, of course, extremely small, but it's still interesting to consider how such a collision would affect the star. If we don't take into account the specific chaos that Jupiter would cause as it breaks through the orbits of the inner planets, the consequences wouldn't be serious enough to blow up or extinguish the star. Actually, the sun's luminosity may increase a bit. The kinetic energy delivered by Jupiter when it falls onto the surface of the star is unlikely to make it look like a pebble thrown into a swamp. Not only light gases will collide during the impact. For example, the giant's iron core is 3 times the size of Earth. In any case, the star will neither go out nor explode. But it's hard to predict the consequences for our planet in such a cataclysm. No matter how you look at it, the idea of destroying the sun is just plain nonsense. It's like sawing off the branch you're sitting on. You can put away the Valerian and finally come out of the bunker. We probably won't destroy the sun in the next few thousand years. There have been people born on Earth who were so intellectually advanced and progressive in their thinking that it seemed as if they had come from the future. Nikola Tesla was such a prodigy. There have also always been people who, for selfish reasons, could let any idea be forgotten, even if it would allow humanity to make an instant technological breakthrough. Nikola Tesla made many discoveries. He predicted the appearance of robots. He demonstrated an experiment on wireless transmission of electricity, and he invented the so-called death ray. His attempts to use the ether were especially mysterious, the all-pervading medium that fills everything that exists. Tesla fiercely refuted Einstein's categorical, possibly paid-for refusal to believe in the existence of the ether. Tesla was amazed at how it was possible to assume that radio waves exist, but the medium that carries them does not. To prove he was right, the great scientist suggested looking at the Michelson-Morley experiment, which supposedly proved that the ether was a fiction from a different point of view. That experiment consisted of detecting the movement of the ether relative to the Earth. It was not detected, and based on this, many scientists abandoned the concept. Tesla, in his manuscripts, proved that this was a hasty and ill-considered decision. Even Aristotle believed in an endless source of free energy. We just need to learn how to use it properly. Tesla knew how to do it. But with his death, the knowledge of the source of universal prosperity died as well. By the way, ether was mentioned in the works of René Descartes, Christian Huygens, and Isaac Newton. Let's present a few theses from the manuscripts of Nikola Tesla. Why is ether so difficult to detect? The scientists claimed that the density of ether is thousands of times greater than that of air. It is known that the density of a substance directly affects the speed at which waves propagate through it. Ether is electrically neutral, so its interaction with the material world is extremely insignificant. In addition, considering such a high density, our world offers almost no resistance to ether. How can an ordinary person feel the presence of ether? It's simple. During rapid acceleration or sudden braking, that is, gravity is actually the manifestation of the ether in the surrounding world. You came from the ether, and to the ether you shall return. Tesla believed that the universe originated from the ether, and that stars and planets are regions of lower pressure in this substance. That is, everything in the world is made from ether. The substance constantly tends to contract, while the material world actively resists this. But when the matter of our universe loses its electric charge, the world will be flattened by ether, which will return to its original state. Why did the Michelson-Morley experiment fail? To prove the incorrect interpretation of the experiment's results, Tesla gives a clear example. Imagine your boat being sucked into a whirlpool. Try to determine the movement of the boat relative to the vortex. You won't notice it because the speed of the water in the boat are identical. If you extrapolate this example, replacing the boat with our planet and the vortex with an etheric hurricane swirling around celestial bodies, then everything falls into place. Ether and the revelation of ancient mysteries. Thanks to a deep exploration of the possibilities of ether, it would be possible to understand how ancient people moved megaliths without any technology. How did the Dogon people know about Sirius? What did the Egyptians use to build and decorate the famous pyramids? And much more from the category of the unexplained. And now the main question: why is it forbidden to mention the ether? Moreover, even now, such scientists are harshly ridiculed by their colleagues. The persecution began at the beginning of the 20th century. The research was suddenly stopped. A lot of artificial obstacles were created, including staff reductions, laboratory closures, and denial of patents. A propaganda campaign was launched to discredit the ether as a source of eternal and, most importantly, free energy. It would seem illogical because this is an opportunity to create a perpetual motion machine, humanity's dream. The indirect culprit behind the emergence of the paradoxical social situation was Tesla himself. His advanced experiments worked wonders. They illuminated the path for ships using ether. A car appeared that ran on infinite eternal energy. The scientist's mistake was that he told the wealthy industrialists about his discovery. For some time, Tesla's progressive projects were even funded, but then everything suddenly stopped. In 1898, Nikola Tesla attached an unknown device to the attic beam of a building and calmly turned on the apparatus. It was an oscillator that made the building itself and its surroundings shake. People ran out into the street in panic. The houses were vibrating. The scientist casually stated that this device was capable of destroying the Brooklyn Bridge, and if the vibrations were calculated precisely and a device of the appropriate size was built, it could even split the Earth itself. Later, realizing the danger of his invention, Tesla smashed the device with a hammer. A car powered by ether. One day, the scientist ordered a limousine to be fitted with an electric motor instead of a gasoline engine and attached a small box to it. The car was tested for a week. It didn't need charging and could reach speeds of up to 150 kilometers per hour. When the astonished spectators asked the scientist what fuel the car ran on, Tesla replied, "On ether," and he didn't explain anything else. The wealthy, who tried with all their might to hold on to power, increase their fortunes, and create a consumer society, realized that the emergence of a free energy resource would put an end to their plans once and for all. As a result of an industrialist conspiracy, the media began a campaign that went down in history as the Overton window. The technique was meant to redefine concepts. Ancient knowledge had to be ridiculed, and even mentioning it had to be forbidden. People who were used to material things refused to accept knowledge about the void, which was filled with nothing. Figures like Einstein began to rise to scientific prominence, successfully steering physics in a completely different direction. The outcome is predictable. In 1920, at a conference in the German spa town of Bad Nauheim, the ether was finally abandoned. As a result, society practically knows nothing about the ether. As an echo of the past, only the expression "to go on the air" remains. The source of inexhaustible energy was forgotten, and the world is filled with extreme poverty and incredible wealth, competition for resources, and consumer markets. All of this is artificially framed by the media as a crisis, although it's simply a struggle for leadership and dishonest competition. We hope that the day will come when the world remembers the ether, as long as it's not too late.